So in the morning class, we have seen how to convert the analog signal into a digital signal. First one is sampling. Sampling will take a discrete analog values. Then it is quantized to a predefined values. Then it is encoded by some method to get a binary level. There are different types of analog to digital converter. One it is flash type. The flash type we have several comparators for different voltage levels. For example, I am having an input voltage of 10 volts and I am using a 3-bit converter. So 2 power 3, 8 combinations. So 10 volts is divided by 8, 1.25 volts. For every comparator, this resistor is chosen such that here it is 8.75, here it is 7.5, 6.75 and so on, like this. So in this here it will be 1.25 volts. For every comparator there is a constant difference of voltages. Here the input voltage is fed to all the comparators. So even though many of the comparators output is high, this priority encoder will take the highest priority input. Remaining inputs, even though it high, it will neglect. Okay, that is the use of priority encoder. For example, the 7 is getting a 1. For 7 is getting 1 at the same time 6, 5, 4, 3, 2, 1. Everything is getting 1, but it will take 7 as the input. So remaining inputs it will neglect. That is the purpose of the priority encoder. So if 7 is high, the output of this encoder is 111. 111. This is flash type ADC. So it is very simple in operation and very fast also, but the resolution is very low, cost is very expensive. So if you want to increase the number of bits, the cost is increased double times, triple times. Next one is dual slope or counter ramp or digital ramp ADC. It is used in digital voltage measuring instruments. Here the comparators are used and there is a capacitor. Initially this capacitor is first charged. So it charged to a particular level. So and then it will discharge. The resist is moved from the battery. So slowly it will discharge. So when the discharge after a certain time, the capacitor voltage will be equal to the reference voltage. That voltage we take the values. That is the digital output. Okay. So when analog value is applied, the capacitor begins to charge in a linear manner and the oscillator passes to the counter. The counter continues to count and it reaches a predefined value. Once this value is reached, counter stops and the counter is reset. The control logic switches the input to the first comparator to a reference voltage, providing a discharge path for the capacitor. As the capacitor discharges, the counter counts. When the capacitor voltage reaches the reference voltage, the count stops and the value is stored in the register. So next one is successive approximation ADC. It is widely used in industries all over many industries. So it is much faster than the older method, digital RAM method, but it uses digital logic to conversion analog logic. So it uses digital logic to convert the value close to the margin. The comparator and a DAC are used in purpose. Even though we are doing ADC, a DAC is also there in the process. A successive approximation register is added to the circuit. A register is added to the circuit. We call it as the register as successive approximation register. Instead of counting up in binary sequence, the register counts by trying all the values of bits starting from the MSB and finishing at the LSB. So in the register is monitoring the comparator output to see whether the binary count is greater or less than the analog signal input and adjust the bits accordingly. So we see how it is working. So this is known as successive approximation register. This is known as successive approximation register. So here the DAC output is given to the comparator. Here the input voltage is given. This input voltage is given to the successive approximation register. Okay. So when the input voltage first very low value 1.25 volt is taken. 1.25 volt is taken. The corresponding bit position is taken. The 1.25 volt will be coming in this DAC. It is compared with the input voltage, and here it is checked. If the input voltage is greater than the this 1.25 volts, then we take the next value. So this second seventh bit is making as 1, remaining bit 0. Now the comparator output will change to 2.5 volts. Then to 2.5 volts is compared with the input voltage. Now if the input voltage is less than the 2.5 voltage, so it is approximately equal to the 2.5 voltage. Like that it will be taken, and the corresponding bits are taken to the SRG, and it is given as binary output. Okay. So this is a principle behind this. So for any ADC, you need a counter. For this counter, you require these flip-flops. Okay. So in this successive approximation ADC, you require a DAC. This DAC will start from the LSB. Then in the input voltage is checked. The input voltage is greater, you go for the next state. That voltage is generated and it is checked. When the input voltage is less than the corresponding reference voltage, we make it as it is a value, and we take the whatever value available in the DAC input of the DAC, we are taking into the SRG and we produce the binary output. So this is analog input. This is the digital output obtained in successive approximation register. So this is a comparison chart between these two resistors. Dual slope resistors. It is very slow, but medium high. Cost is relatively medium. Flash is very fast, but cost is high. Successive medium fast. So our examples of AD2 applications are microphones. It takes your varying pressure voice in the air and convert them into electrical signals. So strain gauges will convert the amount of strain when a stress is applied. Thermocouple temperature measuring devices converts thermal energy to electrical energy. Voltmeters, digital multimeters, and so on. So this is about the A to D conversion. Now D to A conversion. How the D to A conversion is working. So next one is digital to analog converters. Here also there are different types of digital to analog converters are there. So what is DAC? DAC is digital to analog converters. So it will convert a digital signal into corresponding analog signal. It may be a voltage or a current output. So the input is zeros and ones, so the output is a continuous waveform. So what is a DAC? So DAC will produce a corresponding output signal. It will produce an analog output signal corresponding to the digital input signal. So many types of DACs are available. Usually switches, resistors, op-amps are used in movement dispersal. So there are two types of DACs. One is binary weighted resistor Another one is R to R ladder. R to R ladder. Utilize a summing here binary weighted resistor method. So we are using a op-amp circuit which is used as a summer. So weighted resistors are used in order to differentiate the MSB to LSB. Transistors are used to switch between V reference and ground. Okay, this is binary weighted resistor method. So this is the circuit diagram. If you look at this, there is a reference voltage. So in this reference voltage, one end is given, another end is terminal is given for every switch from R to NR. Okay, there is a feedback circuit where the current is multiplied. So voltages V1 to Vn are either V reference or corresponding bit is higher ground. If corresponding bit is low, V1 is more significant bit, V0 is more significant. Vn is least significant. The formula for this binary weighted resistor is IRF minus IRF. RF is a feedback resistor. So I we have to find out. So I, what is the current? So current equal to total B. So every resistor voltage they have given V1, V2, V3 up to V15. So V I out equal to R minus RF V1 by R plus V2 by 2R V3 by 4R plus Vn by Vn minus 1. If, for example, if all the feedback for feedback resistor RF is R by 2, in case, then V out equal to minus RF, which is equal to minus V1 by 2, V2 by 3, V3 by 4, V3 by 8, and Vn by 2n. For example, a 4-bit converter produce a voltage, analog voltage V out equal to minus V reference into B3 1 by 2 plus B2 1 by 4 plus B1 1 by 8 plus B0 160. Where B3 corresponds to B3, B2, B0 and so on. So advantages of this binary weighted resistor method is it is very simple in construction. It will convert the process very quickly. It is simple in conversion and it will convert very quickly. Disadvantages are large range of resistors. Disadvantages are large range of resistors. With the necessary high precision, low resistors. So it requires low switch resistance in transistors. So here the advantages are simple in construction, fast conversion, requires large range of resistors. With the necessary high precision, low resistors also. For these disadvantages, mainly they are using R to R ladder network. Here there is a V reference voltages. Here it is 0 volt. So here the number of resistors are connected in series. In between we are taking resistors. So every bit has a certain voltage. The resistors and R network is connected in such a way that the full voltage is divided into equal parts. So every bit position has a corresponding voltage. Each bit corresponds to a switch. If the bit is high, corresponding switch is connected to the inverting input of the amp. The switch is low, bit is low, it is connected to ground. So after V3, you have a resistor called 2R, then it is grounded. So from V3, it is 2R, it is connected to ground. V3, 2R, it is connected to ground. Next one is R equivalent. Since we have two resistors in parallel, R equivalent we have to find out. R equivalent formula is R1, R2, R1. So here these two resistors are in parallel. So R2R, 2R, 2R plus 2R. So it is equal to R. So it is replaced by a single R. Now we have to find the voltage V3 is equal to R by 2R plus R into V2. R plus R into V2 is equal to 1 by 2 V2, V1. So V3 is equal to 1 by 2 V1, V2 is equal to 1 by 2 V1, and V1 equal to 1 by 2 V reference. V1 equal to 1 by 2 V reference, V3 equal to 1 by 2 V2. Now we are taking in terms of V reference. So in the last case, we are taking V3 in terms of V2, V2 in terms of V1, V1 in terms of V reference. So V3 is half of V2, V2 is half of V1, V1 is half of V reference. Okay. VOD equal to minus IR. Now we are taking everything in V reference. V3 equal to 1 by 8 V reference, V2 equal to 1 by 4 V reference, V1 equal to 1 by 2 V reference. VOD. Now, for a 4-bit R2R network, V have to equal to V minus V reference, V3 into 1 by 2 plus V2 into 1 by 4, V1 by 8, V0 1 by 16. For a general n-bit R2R network or weighted resistor, the formula is V0 equal to minus V reference, sigma I equal to 1 to N, VNI minus 1 by 2. So in the R2R ladder network, advantages is only two resistor values. There are more number of resistors, but only two resistor values are used. Does not require high precision resistors. You does not require a high precision resistors. Finally, the speed is very low. So what are the specifications of DAC? We have seen the two types. So when you specify the DACs, so you have to specify in terms of these following parameters: resolution, speed, linearity, settling time, and reference voltages, errors. Resolution, it is the smallest analog increment corresponding to one LSB change. So if you are changing the LSB, last bit, if you are changing, what is the MSB? That is known as resolution. Okay. So n-bit resolution can resolve 2n distinct analog levels. The n-bit resolution can resolve 2n distinct analog levels. Common DAC has 8-bit to 16-bit levels. Now, next property, speed. How speed the digital data is converted into analog data. This conversion rate depends upon the clock speed of the input signal and the settling time of the converter. When the input is changing very fastly means the speed conversion machine, DAC conversion, speed conversion or DAC conversion equipment should be as made as possible. Then only it is possible. So next property is linearity, the difference between the desired analog output and the actual output over the full range of expected values. Difference between the desired analog output and the actual output over the full range of expected values. So how much it is deviated from the analog value, actual output value and the analog value. So in ideally a DAC should produce a linear relationship between digital input and analog input output. Settling time. Settling time is the time required for the output signal to settle within plus or minus 1 dB for its final value after a given change in input scale. The input is limited by slew rate. of the output amplifier. So ideally, instantaneous change in analog voltage would occur when a new binary word enters into DAC. Reference voltages are there in the DAC. It is used to determine how each digital input will be assigned to each voltage division. The types of reference voltages are given when it is non-multiplier DAC and multiplier DAC. In the non-multiplier DAC, the V reference is fixed. In multiplier DAC, V reference provided by the external source. So what are the types of errors associated with the DACs? These are the different errors: gain, offset, full scale, resolution, non-linearity, non-monotonic, settling time, and overshoot. So gain error occurs when the slope of the actual output deviates from the ideal output. So gain error occurs when the slope of the actual output. So deviates from the ideal output. Actual output deviates from the ideal output. So the gain is changing, the gain error is coming. So offset error means here there is when a constant offset is changing between the actual output and the ideal output. For different values of input, if there is a constant change in actual output and ideal output, they are calling it as offset error. Full scale error. So here also full scale resolution error, poor representation of ideal output. For example, number of bits are used means poor resolution. So this would not be with the connection process. So non-linearity error. So good signal is differential analysis. So here the step stages with increasing digital input. So integral means amount of deviation come from the straight line and offset, and gain errors are removed and considered fixed. This is non-linearity error. Non-monotonic error. Sometimes this error occurs. Normally it will go in a good fashion. Some unwanted signal may become in the middle. That is known as non-monotonic error. When if you increase the digital input, results in a decrease in analog output. That is known as non-monotonic error. Settling time is the time required for the output to fall within plus or minus 1/2 LSP. Overshoot occurs when analog input overshoots the ideal output. So far what we have seen here is digital to analog converters will convert the digital signal to analog signal. Sadly, we are calling as DAC. So input is digital signal 1 and 0, output is a continuous signal. So input is a binary number. So it will be separated by a constant intervals. Many types of DACs are available in the market. The mostly popular are R2R ladder network and binary weighted resistors. These DAC networks are usually made up of switches, resistors, op-amps. So in binary weighted resistor method, you are using a op-amp resistor. So weighted resistors are used to distinguish each bit from the most significant bit to the least significant bit. The transistors So in binary weighted resistor method, we are using an op-amp circuit for summing one. There are weighted resistors connected. The transistor is used to switch between V reference and ground. If it is connected to V reference, it is high. If it is connected to ground, it is low. If you look at the diagram, there is a comparator, there is a feedback circuit. For every resistor, you have a switch. Either it is connected to V reference or it is connected to ground. If it is connected to V reference, it is bit high. If it is connected to ground, it is bit low. So the resistance values are increased the order. So initially the first bit R means next bit it is 2R, 4R, 8R, 16R and so on. So here it is an ideal op-amp. So no current will flow inside the op-amp. Virtual ground is available as the inverting input. So Vout equal to minus F RF. So in a binary weighted resistor method, the voltages V1 to Vn are either V reference or flowing into the corresponding bit. V1 is the most MSB and Vn is the LSB. So Vout equal to minus RF, which is equal to minus RF, V1 by R plus V2 by 2R plus V3 by 4R up to Vn by 2n minus 1 R. So if RF and R2 are equal, then we have to equal to minus VR, V1 plus V2, V2 by 4, V3 by 4 into A, n by 2n. So advantages of binary weighted resistors are it is very simple, it is very fast, it requires larger resistance, it requires switches resistance, it is very cost. Next one is R2R ladder network because in the upper side you have R, in the parallel side you have 2R. So the 2R is connected to every bit. Here also, if it is connected to the inverting input, it is known as bit is high. If it is connected to ground, it is 0. Okay. If the bit is high, the corresponding switch is connected to the inverting input of the amp. The bit is low, it is connected to the ground. So in the last stage, you have a 2R resistors, both 2R resistors in parallel. So we are simplifying it. By simplifying this R2R network, we get V3 equal to 1 by 2 V2. Then V2 is equal to 1 by 2 V1 and V1 equal to 1 by 2 V reference. Vout equal to minus R. So this is about Vout. So everything is right in terms of V reference. 1 by 8 V reference, 1 by 4 V reference, 1 by 2 V reference. For B3 it is 2R. When it comes to B2 it is 4R. 2R plus 2R. Then for B1 you have to multiply by 2, 4 into 2, 8. Then 8 into 2, 16 and it will go such as. Where B3 corresponds to bit 3 and B2 corresponds to bit 2. Bit n is set means Bn equal to 1, bit n is clear means Bn equal to 0. So this is the formula for the R2R ladder. The advantages is only two resistance values are used, R and 2R. Does not require high persistent resistors. High persistent resistors not needed in this case. So disadvantages it is very slow. So these are the terms for tags, resolution, speed, linearity, settling time, reference voltages and errors. Resolution is them for one LSB change, what is the change in the output? That is known as resolution. So speed is how fast it is converting the analog output to the digital input. That is known as digital conversion. So next, the conversion rate depends upon the clock speed, settling time. When the input changes rapidly, the DAG should also be speed should be high. Linearity means what is the difference between the desired output and the actual output obtained. So linearity means the input changes, output also changes. Here it is changing. Settling time means the time required for the output to settle within plus or minus 1.5 LSP. It is controlled by the slew rate. Reference voltages are everywhere in the DAC to check whether the put is a correct voltage. So these are the errors: gain error, offset error, failed error, solution error, non-linearity, non-monotonic, selling time, and overshoot. So gain error means actually if the output is high or low. If it is deviating, then you have to find the difference and you have to divide by the original output and you have to multiply by 100 gain error. So offset error means for every input, output changes for a particular level means it is known as offset. For full scale error, the output is a different one from our end. Then it is a full scale error. The solution error, it is a poor representation of the ideal output. The size of the voltage divisions affect the resolution. For non-linearity error, this occurs when the output signal is non-linear. It may be a differential output signal or a integral output signal. Then the output is different. Then there is no relationship between input and output. Then it becomes a non-linearity error. Non-monotonic error means if you suddenly increase the input, output also increase. This is known as non-monotonic input. So finally, it is settling time and overshoot. Settling time is the time the output should remain in this state within the plus or minus 1 by 2 LSB. Then the output is constant, our output is good also. The overshoot occurs when analog output overshoots the ideal output. So applications are digital motor control, computer printers, sound equipment, electronic cruise control, and digital thermostat. மேல போய் பாருங்க ஆக்சுவலி ஃபர்ஸ்ட் ஃப்ளோர். So this is all about DAC. We see ADC and DAC. So these are theory questions only. There is no design problem. So you may have to write R2R network. You may have to write binary weighted resistor network, dual slope ADC or successive approximation ADC. Any one theory question may be coming. So you have to write accordingly. So next about is synchronous counter. So in the morning we see asynchronous counters. Now we have to see synchronous counter design. Okay. Similarly, in up counter, down counter, then modulus counter, we have to do in synchronous also. So the circuit connection is somewhat different when compared to a synchronous counter. We see how it is working. One option. 108 also option. Afternoon 1, 2, 3, 4, 5.
Sir.
Yeah.
Sir, I have mentioned your absentee, sir.
Yes, sir. Yes, sir. So afternoon means.
Absent.
Okay, no problem. So we are going to see synchronous counter, up counter, then down counter, then modulus counter. First we see synchronous up counter. So in the synchronous up counter, they are using 3 flip-flops. They are taking a 3-bit. So it is also JK flip-flop only. So it is connected in T mode, toggle mode. So in this case, the clock is common. For synchronous counter, the clock is common. So since clock is common, we are calling it synchronous. Okay. Here J and K are connected together. Here J and K are connected together. But this output, first flip-flop, it is connected to plus 5 volt. Second flip-flop, it is connected to the QA output. Second flip-flop, it is connected to QA output. For third flip-flop, it is connected via A and gate. The inputs to the AND gate are QB and QA. QA and QB. For next flip-flop, if it is there, input is QA, QB, QC. So it will have all the flip-flop outputs. Okay. This is JA, this is KA. JB, KB, QB. JC, KC, QC. Okay. So these are the outputs. QA is the output, QB is the output, QC is the output. These three are. Okay. So in the asynchronous counter, J and A, all the JK inputs are connected to plus 5 port. Here, only first flip-flop is connected to plus 5 port. Remaining flip-flops, it is taken from the previous outputs. A and K connected from A. For third flip-flop, it is connected with the outputs of first and second flip-flop. If it is there is another flip-flop, the inputs are first flip-flop output, second flip-flop output, and third flip-flop output. So all the three flip-flop outputs are connected to as inputs to the AND gate. That output is given to the fourth flip-flop. So here also, first we draw the timing diagram, then we draw the truth table. So I am drawing the timing diagram. So clock. So this is the clock. So first flip-flop is a toggle flip-flop. It has no problem. It is continuously given plus 5 volt. So it will toggle at every clock pulse. So it will toggle at every clock. QA will toggle at every clock pulse. So at the negative edge of the clock pulse, it will toggle. But this is QA, no problem. QB. So QB will toggle the output when J and K is 1. When will be J and K will be 1? When the QA is 1, J and K will be 1. Okay. When QA is 0, J and K will not be 1. So these two conditions, J and KB should be 1, as well as the clock should be negative edge. So QA should be high, as well as clock should be negative edge. So here it is 0, now it is 1. So in this there is no negative edge, here it is negative edge, but it becomes 0. Okay. Now it is 1. This stage, we look at this stage, clock is 1. During this stage, clock is 1. So QA is 1 and it is negative edge. So QB will change at this point. So when JB and KB is 1 and the clock during the negative edge of the clock pulse, QB changes. When JB and KB will be 1, QA is 1 only, JB and KB will be 1. So here JB and KB is 1. Now there is a negative edge, so QB will stop. Then it will go like this. So once again here it is 1. So here it is a negative edge, so it will stop. So once again here there is a negative edge here, so here and here it will go. So I have done a QB. Now QC. QC will toggle the output when JC and KC is 1 and the clock should be negative edge. When it will be 1, QB should be 1, QA should be 1. QA should be 1 and QB should be 1 and the negative edge of the clock. Then only QC will toggle its output. Here QA is 1 but QB is not 1. It is reaching only. So it is 0 only here. Here it is 1 but it is 0. So it won't work. Here 1, there is a negative edge. So here QC will change here. Then here it is 0, here 1, 1. So there is a negative edge, here it is change. Okay. So now draw the random values 0, 0, 0. Here it is 1, 0, 0. Now it is 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0. Once again, the cycle starts. Here also you get the same states what we are getting in asynchronous motor, but the circuit connection is different. There is no delay happening in this counter. So in asynchronous counter, there is a delay happening. Here there is no delay happening in the synchronous counter. That is the advantage in synchronous counter. Okay, now we can write the truth table. Truth table. So before first state it is 0, 0, 0. 0, 0, 0. Now it is lowest, QA is lowest, QB and QC. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So this is the truth table for this particular counter. So this flip-flop will toggle only JB and KB is 1. When it occurs, QA is 1 only, this will occur. So QA should be 1 and there should be negative edge. Then only this will toggle. Similarly, this will toggle when JC and KC is 1. So this will happen only when QB and QA is 1. Both are 1 and during the negative edge of the clock pulse, it will toggle. So in this case, so QA as well as QB is 1, there is a negative edge, it is toggle. Here also QA and QB is 1 and there is a negative edge, it will toggle. So after drawing this, you write the truth table, that's all. This is synchronous up counter. For down counter, you have to give the AND gate lower. So instead of QA, you have to give QA bar as input. Similarly, instead of QA QB, you have to give QA bar and QB bar as output. Control input. So write down. So first flip flop input 5 volt, second flip flop input is QA, third flip flop input QA and QB. Clock is common to all the flip flops. So all the flip flops will change its outputs at the same time. That is why we are calling a synchronous motor. So J and K, it is always 1. So it will toggle at every clock pulse, negative edge of the clock pulse. So JB, QB will toggle when JB and KB equal to 1. So J and KB is depends upon QA. QA equal to 1 and during the negative edge of the clock pulse, it will toggle. And JC, QC will toggle when JC and KC equal to 1. It depends upon QA and QB. QA as well as QB should be 1, and during the negative edge of the clock pulse, it will. So we get 8 clock pulses, 8 states, 0, 0, 0, 2, 1, 1, 1. Then once again the same cycle continues. So it is a 3-bit counter, so 2 power 3, 8 states. So it will count from 0 to 7. It will count from 0 to 7. Okay, shall I move to the down counter? Down counter. So it is the same output only, slight modification. Same circuit only. So the control circuit is different. This control circuit you have to change it. Remaining things same output QA, QB, QC only. Output is same. QA, QB, QC. Here there is no control input like this. So you take QA bar, QB bar. QA bar is connected to JNK. QA bar is connected to JBKB, and you have a AND gate. QA bar is one input, QB bar is another input. It is connected to JCK. That's all. This is down counter. This is down counter. What I am doing is I just change the control input from QA to QA bar for second flip flop, and for third flip flop I am changing QA QB to QA bar QB bar. Now the output automatically changes. If you draw the timing diagram, put completed. For that I will move to the next timing diagram. Joined. Have we completed the timing diagram so that I can move to the next timing diagram? So let's repeat the second one, right hand side. So they will ask a 3-bit or 4-bit. Sometimes they will ask 5-bit synchronous counter. Then you have to draw the timing diagram for QA, QB, QC, QD, QE. Then you have to draw 5 flip flops. For fourth flip flop, you have to put a 3-input AND gate, and you have to give QA, QB, QC. For fifth flip flop, you have to use 4-input AND gate, and you have to connect QA, QB, QC, QD. So if the number of flip flops increases, you have to add the number of input in the AND gate, because you have to start from QA, QA, QB, you have to give QA input to all the flip-flops you are connected successfully. So since we have QA bar, QB bar, we have to draw this diagram also for down counter. So without drawing QA bar and QB bar, we are just confused. So while drawing QA, we have to draw the QA bar, and QB bar also we have to draw. Then only it will be easily understood. The clock signal is same. So first flip-flop QA, the connection is same only for up counter as well as down counter. This signal connection is same because plus 5 volt is connected to JA, KA. QA is output, the same output from up counter. So QA diving diagram is same only. Then QB and QC will change. Automatically it will change. Okay. So you have completed. So for down counter, you draw the QA bar and QB bar. Then only it will be easy. So QA bar, first I am drawing QA bar, the opposite of QE. So initially it is high. So it is the inverse diagram of QE. Okay. So I have drawn the QA bar. Now I have to draw QB. So sorry, QB. So QB, the input is taken from QA bar. So depending upon the input in QA bar, the second flip-flop toggles. So initially it is 1. QA bar is 1. There is a negative edge. So it will change here. Okay. It will change here. The starting point it will change during this negative edge. Next, when it becomes positive edge, here QA bar is high and there is a negative edge. So here it will go low. Once again, in this point it will go high. This point go low. Once again, this is go high. This is QB. Okay. So second flip-flop toggles when QA bar is high and during the negative edge of the toggles. Here the QA bar is high and there is a negative edge, it toggles. Here QA bar is high and there is a negative edge, it toggles. QA bar high, negative edge, toggles. QA bar high, negative edge, toggles. Similarly, QA bar high and negative edge. Now we have to draw the QB bar. QB bar. It is the opposite to QA. Okay. For the third flip-flop, you have QA bar and QB bar is connected to AND gate. So QA bar should high, QB bar should also high. QA bar should high, QB bar should be high, and there is a negative edge. Then only it will target. So QC, initially it will target because QA bar is high, QB bar is high, so it will target to 0 to 1. Now QA bar and QB bar. QA bar here high, here not there. QA bar here it is high, here also high. So it will toggle here. Now here not possible. Here QA bar high, here also QA bar high. So in this case, it will toggle. Okay. Now you have to write the numbers, zeros and ones. So you have to write only in QB QC. So 0 0 1 1 1 0 1 1 0. Sorry, no. Here 0 1 0 1. And now here, here 1 1 0 0. Here everything is 0. Once again here it is 1 1. So it is a down counter because it starts initially it is 0. Doing out of the first clock pulse it is 1 1 1 7. Next it becomes 1 1 0 6. 1015, 1004, 0113, 0102, 00011, and 000. It is 0. So it starts from 7 and slowly counting down 6, 5, 4, 3, 2, 1. Okay. 0 once again start with 7. So this is a down counter. So only thing difference between up and down counter is the up counter you are giving the control of the next flip flop from QA, QB, QC and so on. Here we are taking the control from the complement. In asynchronous counter, there is no change in the circuit. Only change you have to take the output in complement to get the down counter. But here you have to change the circuit in such a way that control is taken from ordinary inputs to complementary inputs. So now you have to write the truth table. Truth table. So initially it is 0, 0. So first clock pulse it is 111, 110, 101, 100, 011, 010, 001, 000. Okay. This is the truth table for this counter, synchronous down counter. So I have changed the control from QA to QA bar, similarly QB to QB bar. So first flip flop QA bar, second flip flop QA bar and QB bar, added together. So while drawing the timing diagram for synchronous down counter, you draw the QA bar and QB bar. Then only you can easily draw the diagram. Then it is understandable also. If you doesn't draw QA bar and QB bar, you will confuse. So whenever you are designing a down counter, you draw the corresponding signals also. Then it will be very easy. So the next one is modulus counter. To finish the diagram, I will write. So like this, they will ask 2-bit synchronous up counter or 3-bit synchronous down counter up to 4-bit. So they will ask up counter or down counter, whatever counter. If they doesn't mention any up counter or down counter, you draw only up counter. They mention, you draw the corresponding counter. If they doesn't tell any value, if they tell design a synchronous counter means you always draw the counter. So up counter is down counter if they specifically draw it. Otherwise, don't know. So after the smaller counter chapter is over, the four is completed. Test on it objective type. Objective type. So I will give one more assignment in this digital electronics. Those
Hello, sir.
you can take hello? Hello?
No, nothing, sir.
Nothing, okay. So if anyone want to do seminar, you can contact me. But the assignment and the unit test is you have to do everything. So I go to modulus counter. Okay. So I am designing a modulus decade counter. So normally they will ask a question called design a decade counter, decade synchronous counter. So what is decade counter means? It is a counter which will count 10 states 0 to 9. So it will count 10 states, that is known as decade. So for these 10 states, we cannot use 3 flip-flops because 3 flip-flops will count up to 7. Then what we have to do? We have to go for the next higher order flip-flop, 4 flip-flops. So they are not mentioning up counter or down counter, you take up counter. Don't use down counter. So I'm using 4 flip-flops. I'm using 4 flip-flops. Flip-flop 1, flip-flop 2, flip-flop 3, and flip-flop 4. So first flip-flop J and K inputs are plus 5. J, K. So the clock is common. Hence it is a synchronous counter. Synchronous counter is common. For JB and KB, it depends upon QA. For JC and KC, it depends upon AND gate, QB and QA. QB and QA. That is given as JC. For next flip flop, it depends. There is one more AND gate. You take this. It is QA and QB. You take QC also, and you connect to this JD and KD. 2D. So QA, QB, QC are D are outputs. Now it will count from 0 to 15. 2 power 4, 15 states. So it will start from 0. It will count 1, 2, 3, 4, 5 up to 15. Now I want to count only to 0 to 9. So when it reaches the state 10, I will to reset the circuit. For this you will need a reset circuit. So every flip flop has a reset switch. So you have to connect a reset switch commonly to a AND gate. So what are the inputs to this AND gates? So when it reaches 1 0 1 0. So when it reaches 1 0 1 0. This is the trans state 1 0 1 0. Then I have to reset. So it can be written as, so here QA is the LSB. QA is the LSB. This is QB, QC, QD. QD is the MSB. Okay. So QD, QC bar, QB, QA bar. This is the input. QD, QC bar, QB, and QA bar. If it is 0, I have to take the inversion. If it is 1, I have to take as it is. So QD, QC bar, QB, QA bar. So QD is here. So one input is QD. This QD. Next one is QC bar. Here there is QC bar. You take here. This QC bar. Next one is QB. Take this input. This QB. Similarly, QA bar. Here it is QA bar. Take here QA. So it will count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when it reaches 10, this AND gate will have a high output and this will reset all the flip flops to 0. So it will count from 0 to 9 and whenever it reaches 10, it will stop. And it will reset to 0. So once again it starts from 0, 1, 2, 3 up to 9. So this is the modulus counter. It is also a modulus counter. But they will tell design a decade synchronous counter means decade means It is 10. You should understand it is 10. It will count 10 states 0 to 9. So it is a up counter only. It is not down counter. So decade synchronous counter means you have to count 0 to 9. Then you have to use the modulus technique only. Okay. I am using this. So any doubt in this modulus counter? So you have to write the binary state of the value. For decade means it is 10. If it is mod 7 means you have to write the binary value of the 7. Then you have to write if it is 1, you take as it is. If it is 0, you take the complementary output. Then you connect to an AND gate. So that AND gate output should be connected to all the reset buttons. So when it is 1, all the flip flops should be reset and it is become 0. This is the principle behind modulus counter. So we have designed a half adder, full adder. So if we want to design a adder, which will add 4 bits at a time. So half adder will add 2 bits at a time, 2 single bits. Then full adder will add 3 bits at a time. So I want to add 4 bits at a time. So I want to add A3, A2, A1, A0. Similarly with B3, B2, B1 and B3. I have to add this. Okay. So while adding this carry should go here. So while adding this, will carry should go here. Carry should go here. How to design this? So which circuit I have to use for this operation? So I have to add A naught, B naught. There may be a carry or may not be a carry. The carry should be added with A1, B1. Here also a carry into B2, and carry A3, B3. So you have to separate each bit. Here only 2 bits. So I am using a half adder. HA. So input is A0 and B0. So there will be a sum and carry. This is sum. Yes, not. I take it as yes, not. There is a carry C0. Next input. For this bits, it is A1, B1. This is the input carry. It gets the output carry C1. It gets the sum S1. Similarly, this is full adder. This is another adder, full adder. Finally, another full adder. So this is A2, this is B2, this is C2, it is S2. This is S3, C3, A3, and B3. So, this circuit will add 4 bits at a time. So, in our computer, if we are giving a variable A plus B, C equal to A plus B, print C. Then, so A has a word length of 64 bit. B has a word length of 64 bit in modern computers. So you require 64 full adders and 64 full adders for doing this operation. For adding two numbers A and B in this system, computer system. I have taken only 4 bits, but it is nowadays the computers are 64 bit and 32 bit. If it is a 32-bit computer, you have to use 32 full adders. If it is a 64 bit, you have to use 64 full adders. So the circuit complexity increases when you go for the higher number of bits. So if you go for higher number of bits, the precision is very good, but the circuit complexity goes on increasing. So this is for single to 4-bit adders, 4 bits adding. So you know half adder, you know full adder. So with the help of half adder, full adder, I am adding 4 bits here. Right. If I have to add 2 8 bits, I have to use 4 full adders once again. So 7 full adders and 1 half. Like this, you have to increase the circuit. This one more topic is complement. One's complement, two's complement, or that. So what is one's complement? So suppose I have a word a function. So y equal to 1 0 1 1. My complement number is one's complement of y equal to, so 1 becomes 0, 0 becomes 1, 0 0. This is the one's complement of y. If I want to find two's complement, I have to add 1 with one's complement. One's complement plus 1. Plus 1. So 0 1 0 0 plus 1 is equal to 0 1 0 1. This is the two's complement for this particular number. Why this complement are required in digital electronics? So in digital electronics, there is no subtractor. So everything is done addition. So by using complement addition, we are doing the subtraction. For this purpose, they are defined develop one's complement and two's complement. For example, I'm taking a subtraction. First, I am doing with one's complement. So I want to subtract 1 0 1 1 with 0 1 0. This is the number I have to subtract. For this, I am taking the second number, one's complement, and then I am adding with the first number. So I am taking this is first number, this is second number. I am taking one's complement of second number. One's complement of second number. It is 1 0 0 1. 1 0 0 1. So first number is 1 0 1. I am adding both this 0 1 0 1 1 0 0. Now 0 1. Okay. Oh, there is a final carry 1. So 1 0 1 1 means its equivalent decimal is 8 2 1 11. Here it is 6. 11 minus 6 means it is 5. Final result is 5. So in one's complement, if you are having a carry, you have to move here. And you have to add it. 0 1 0 1. So which is equal to 5. So this is the final answer. So I want to subtract 1 0 1 1 So 0, 1, 1, 0 should be separated from 1, 0, 1. So first I am taking a 1's complement of this number. I am getting 1, 0, 0, 1. Then I am adding with 1, 0, 1, 1. So I get a value of 1, 0, 1, 0, 0. So there is a final carry. So I am moving this final carry here and you have to add it. If there is no final carry, you will leave as it is. Here if it is a final carry, you have to move downwards. Okay. And you have to add it, you get a value of 5. That is the answer. Similarly, if you do in 2's complement, so same number 1, 0, 1, 1, 0, 1, 1, 0. I'm taking 1's complement of second number. It is 1, 0, 0, 1. Then I have to add for 2's complement. 2's complement. 1, 0, 1, 0. 2's complement of number. Now I have to add with the first number 1, 0, 1, 1. It is 1, 0, 1. Here 0 and 1. So in 2's complement, you have to cancel this final carry. And you have to take as it is. Now it is equal to 5. So either you can use 1's complement or you can use 2's complement. So first one, there is a final carry in 1's complement. So I am moving the final carry to the LSB and I have added and I get the answer of 5. In 2's complement, I have already ordered here 1. So if there is a final carry, I have to neglect it, take it the remaining value which is equal to. So all the operations in binary are done by 1's complement and 2's complement for binary subtraction. So binary subtraction is done by complement addition. Binary subtraction is done by complement addition. Similarly, for multiplication also, it will be done by repeated addition. So it will be done by repeated addition. So all the operations are finally depends upon the addition. Okay. So addition is the basic for all operations. So up to this unit 4 is completed. So next class onwards we have unit 5, it is communication systems. So what are the communication systems available in the today's as well as the earlier days? So because not only today's, in earlier days communication also there it is given in the syllabus. So when you know about television, radio, fax machine, microwave communication. So what is microwave communication? You doesn't know. Many of the people doesn't know what is microwave communication. So microwave communication is a method of communication. So they transmit the microwave from one place to another. For every 30 kilometers, they keep the tower. The signals are transmitted through these towers. If one of the tower fails, means the linkage is broken. So for every 30 kilometers, they will place the towers. All the signals are transferred through these towers. These towers are kept at a height of nearly 100 meters, very high. So it will keep very high. Then only it can absorb the signals from the other towers. So this is microwave communication. Then comes satellite communication, and so on. So these there are 6 topics of communication. Then we see what is modulation, what is amplitude modulation, what is frequency modulation, and phase modulation. So amplitude modulation means we are changing the amplitude of the carrier wave. Frequency modulation, we are changing the frequency of the carrier wave. Phase modulation means we are changing the phase of the carrier wave. So what are the types of modulation techniques they are using? And we see the 6 different types of communication. That is 5th unit. So after that we have a revision class. If we complete the portion, we have a revision class for extra classes. So any doubt in today's class in counter design, modulus counter, up counter, down counter, synchronous and asynchronous counters. So this design problem will be surely will be there in the question paper. So you should know how to design a counter. Then in the this is sequential circuits. In combinational circuits, they will mostly ask simplify a equation. Then you have to draw the logic diagram, or you have to expand the equation. Like this, they will ask. Alternate recommended level. Mohammed Ijaz, are you there? Mohammed Ijaz. Always not there. So first unit you have circuit theory, second unit missings, third unit electronic devices, fourth unit digital electronics, and fifth unit communication systems. So this is the basics of EEE subject. Not only EEE, it is basics of ECE or electronics communication also there. So I have corrected your papers. I have written your papers in Google Classroom. Many of you have not written true questions. Why? And not written well also in some people. Mark is reduced up to 5 marks for many persons. Why? Gautam K. Gautam K. Mark பார்த்தீங்களா?
Sir,
Have you seen the mark?